A moving point in the sky does not need to be dramatic to be meaningful. It only needs to be measured more than once. The first detections arrive as separate images taken minutes apart, then as another set taken hours later, then again on a different night. In each image, the stars hold their positions relative to one another, but the point shifts. At first, the shift is small and uncertain because the object is faint and the sky background is bright with noise. The object's light is spread by optics and by the atmosphere into a blurred spot. Software estimates the center of that blur and records a position. The position is not a guess. It is an estimate with an uncertainty built from the distribution of light across pixels and from the calibration of the image against a star catalog. When another image is taken later, the same process produces another position. Linking those positions across time is the start of the story. The title says the path does not look random. That statement can be true in a simple sense, even before anything special is known. Random motion would produce a scatter of positions with no coherent direction. The sky does not usually behave that way for real bodies. Real bodies follow deterministic paths set by gravity and by their initial velocity. Even a small body that is pushed gently by sunlight and by outgassing still follows a coherent trajectory. Therefore, the first reason a path does not look random is that it is a real object, not an artifact. Yet there is a second layer. Early observations can contain artifacts. Cosmic rays can strike a detector and create bright pixels. Satellite trails can cross an image. Noise peaks can mimic a faint object. Therefore, surveys use linking rules to separate real motion from chance alignment. A real object will appear in multiple exposures with consistent motion. Its motion will be smooth enough that a simple model can connect detections. The earliest model is often a straight-line motion on the sky over a short interval. Over minutes or hours, many solar system objects move approximately linearly because the curvature of their path is small over that short time. If the positions align along a line with consistent speed, that supports reality. If they do not, the detection may be discarded. Once the object is recovered on a second night, the non-randomness becomes stronger. A random noise source would not reappear in a consistent new position. A real object will because it continues moving. At this stage, the work is not about meaning. It is about keeping the object in view. Observers report the positions to coordination centers that collect data from many observatories. A preliminary orbit is computed. This orbit is still uncertain. Over a short arc, many different three-dimensional trajectories can project to similar two-dimensional motion on the sky. The object could be closer and moving slower or farther and moving faster. The model parameters are correlated. But even with that uncertainty, the orbit provides a prediction of where the object will be on the next night. That prediction includes an uncertainty region, often an elongated patch on the sky. Telescopes search that patch and try to recover the object. Each recovery tightens the orbit. This tightening is itself a transition from apparent randomness to structured path. Early predictions can be off because the orbit is uncertain. Later predictions become accurate because the orbit is constrained. To an observer comparing early predictions to later measurements, the object might seem to deviate in surprising ways. In reality, the model is improving. Therefore, the first caution in this story is that a path that looks non-random can be non-random for two different reasons. It can be non-random because the object follows a deterministic trajectory. It can also appear to become more structured because the orbit solution converges as data accumulates. Both are normal. In a disciplined account, one does not interpret convergence as physics. One interprets it as improved knowledge. The measurements themselves have layers. Astrometry begins with identifying reference stars in the same image. A catalog provides their coordinates. The image is solved mapping pixel positions to sky coordinates. The object's centroid is measured relative to that mapping. If the star catalog has small systematic errors in that part of the sky, the astrometry can be biased. If the image has distortions that are not perfectly modeled, the astrometry can be biased. If the object is close to a background star, the measured centroid can be pulled. If the object has a faint coma, the centroid can be pulled by asymmetric dust. These biases can create apparent patterns in residuals later on, yet they do not usually destroy the non-randomness of the overall path. They introduce small deviations around it. In the first region, those small deviations are not yet the focus. The focus is that the object can be linked and recovered, and that the path on the sky can be predicted. The first orbit solutions often assume gravity only. The Sun's gravity dominates. Planetary perturbations may be small over a short time, but are included in modern computation. The preliminary orbit yields parameters that specify the trajectory in 3 dimensions. It also yields a distance estimate. Distance is crucial because it sets how the object's angular motion translates into linear speed. A nearby object can move quickly on the sky with modest linear speed. A distant object can move slowly on the sky while still having a large linear speed. As more observations are added from different Earth positions along Earth's orbit, parallax helps constrain distance. The observation arc lengthens. The object's motion on the sky begins to show curvature as the line of sight changes and as the object's path through space bends under gravity. That curvature is another reason the path does not look random. It follows a smooth arc, and the arc's shape is predictable. The title emphasizes that it does not look random, and at this stage that statement can be grounded in simple geometric fact. A real body under gravity produces a continuous trajectory. The observed sky positions are samples of that trajectory. When plotted, they fall along a curve rather than a scatter. But there is another subtle sense in which a path can be said to not look random. The incoming direction can be consistent. If the orbit is found to be unbound, the object may be classified as interstellar. In that case, the incoming velocity vector is a property of the object's prior motion through the galaxy. One might be tempted to see pattern or intention in that direction. In a conservative scientific account, the direction is treated as a vector, not as a message. It may align with certain structures in the galaxy simply because of the Sun's motion and the distribution of ejection velocities. It may not. In this first section, the story does not go there. It remains at the level of how the first track is built, how multiple nights of data turn a faint point into a coherent trajectory, and why that coherence is expected for any real object. The non-randomness begins as a practical property used to confirm that the object is real and to keep it from being lost. The meaning comes later if residuals remain after gravity is modeled, and if the orbit implies a special category, such as an interstellar origin. For now, the object is simply a moving point. Its path is a measured line that becomes smoother and more predictable as the record grows, not because the object changes, but because the uncertainty shrinks, and because the sky, once measured carefully enough, reveals that motion in space is law-like, and that a true track across stars is almost always the first sign that randomness has been left behind. Not random can be said in many ways, and this section stays with the cleanest meaning, the difference between chance and determinism. In the sky, chance produces isolated points that do not cohere across time. Determinism produces a path that can be predicted from a small set of conditions. The motion of small bodies is not random in the way that noise is random. It is governed by forces, mainly gravity. The only randomness in the physical sense comes from what is not being modeled or from what is not being measured well. The first act of science in this context is to decide which kind of randomness is present. Is the scatter in measurements random noise around a true path, or is the path itself behaving unpredictably because a force is missing from the model? The second act is to define what counts as structure. Structure means repeatability. If a certain kind of offset appears again and again under similar conditions, it is structure. If it appears and vanishes with no pattern, it is more likely noise. In orbit determination, the language of structure is residuals. Residuals are the difference between observed positions and predicted positions. Random residuals cluster around zero with no correlation in time. Structured residuals show trends, cycles, or correlations with geometry. The non-randomness of the overall path is expected, but non-randomness in residuals is the key to deeper interpretation. Before reaching residuals, it helps to hold a simple picture of what determinism means here. If the initial position and velocity of an object are known, and if the gravitational field is known, the future position can be calculated. Small errors in initial conditions lead to small errors in prediction over short times, and to larger errors over longer times. But the relationship remains governed by the equations of motion. This is why early orbit predictions can be uncertain. The initial conditions are not yet well constrained. An observer might say the object is moving unpredictably because the predicted point on the sky shifts as the orbit is updated. But that is not the object being random. It is the estimate being uncertain. This distinction is central in a calm narrative because it prevents the story from treating uncertainty as mystery. The sky provides only angular positions. Converting these into a three-dimensional trajectory requires distance. Early-on distance is poorly known. The same sequence of angular positions can be explained by different distances and speeds. As observations accumulate, especially over days to weeks, as Earth moves, the geometry provides parallax and curvature that constrain distance. When distance becomes better known, the orbit becomes less ambiguous and predictions settle. This settling can look like a hidden pattern being revealed, but it is simply the improvement of constraint. Another kind of apparent pattern can come from observing cadence. If most observations are taken at similar times each night, the sampling of rotation-driven brightness changes or coma asymmetries can be biased. This can create periodicities in measured positions that reflect observing geometry rather than true forces. Therefore, even when structure is detected, it must be tested against observing patterns. A truly physical non-randomness should persist across different observatories, different times, and different reduction pipelines. A non-randomness tied to observing cadence may not. This is another reason the word random must be treated carefully. There is randomness in photon noise. There is quasi-randomness in atmospheric seeing variations. There is systematic error that can masquerade as structure. The goal is to separate these layers. In the context of a small body like 3I/Atlas, the deterministic backbone is the gravitational trajectory. That trajectory is a conic section, an ellipse, parabola, or hyperbola depending on energy. Within the solar system, most bodies are on ellipses. Interstellar visitors are on hyperbolas. In either case, the path is smooth and the curvature is set by gravity. When observers say the path does not look random, they often mean that it resembles such a conic. The orbit can be fit, and the fit produces a coherent arc across the sky. This is important because it demonstrates that the object is not an artifact. It also allows classification. Yet the deeper scientific interest begins when the fitted conic does not fully capture the data. Then the residuals show structure. Structure in residuals can come from a missing force. It can also come from how the measurement is made. For comets, the most common missing force is outgassing. For small fragments, sunlight forces can matter. For dusty objects, centroid bias can matter. The concept of randomness then shifts. The question becomes whether the structured residuals are themselves deterministic in a physical sense. Outgassing produces forces tied to sunlight and to rotation. Radiation pressure produces a force tied to the sun direction. Thermal recoil produces a force tied to rotation and to thermal lag. Centroid bias produces offsets tied to coma and tail geometry. Each has a signature. If the residual structure matches one signature, the non-randomness is explained by a deterministic mechanism. If it does not match any, the explanation is not yet found, but that still does not imply that the object is random. It implies that the current model and the current data are not yet sufficient. The ordinary way this plays out is that structure appears in early residuals, then changes as data quality improves, and as the orbit fit incorporates more physics. Often, what looked like an anomalous pattern becomes consistent with a small non-gravitational term once the observation arc lengthens. In other cases, what looked like a non-gravitational term disappears once contaminated measurements are removed or once nucleus-centered astrometry is used. Both outcomes are common. Therefore, the phrase "does not look random" is best treated as an invitation to careful modeling, rather than as a hint of intent or a hint of impossibility. The path is structured because gravity is structured. Any additional structure is either additional physics or additional measurement effects. There is no need to import other meanings. Another way to make the same point is to compare two kinds of unpredictability. One is chaotic sensitivity, where small uncertainties grow over time, making long-term prediction difficult, even though the system is deterministic. Small body trajectories can show this over long times due to planetary encounters. But over the span of weeks or months, the motion is generally predictable. The other kind of unpredictability is lack of constraint, where the data are insufficient to determine the orbit well. That is the early discovery regime. The object's true path is not random, but it is not yet known precisely. That lack of knowledge can look like irregularity. This section keeps the story anchored in the second kind. As more data arrives, the orbit becomes known better. The non-randomness of the path is not a revelation about the object's nature. It is a reflection of how measurement accumulates into constraint. The practical consequence is that one should be slow to assign significance to early apparent patterns beyond the gross fact of a coherent trajectory. The significance comes when patterns persist after the basic uncertainties are reduced. Persistence is the test. If a drift remains in residuals after the orbit is tightly constrained, then a force is implied, or a systematic bias remains. If a drift does not remain, then the early pattern was an artifact of uncertainty. In a calm documentary voice, this is not disappointment. It is the normal outcome of careful work. The sky is full of moving objects, and most of them follow paths that do not look random because their motion is governed by gravity. The interest in a specific object comes from what remains after that obvious structure is accounted for, whether there is a small extra drift beyond gravity, whether its direction and distance dependence match known mechanisms, and whether the same pattern is seen by many instruments. Only then can the phrase "not random" carry its deeper meaning, not as an emotional reaction to a curve on a plot, but as a quantified statement that the measured points require more than the simplest model, and that the additional requirement itself has a form that can be tested, constrained, and either explained or dismissed one careful night at a time. Gravity draws the curve, even when nothing else is known. This section stays with that curve as the outermost physical layer, because it is the reason a path across the sky looks ordered rather than random. Solar gravity is central. The sun's mass dominates the solar system, so the gravitational field near the sun is largely set by the sun. A small body entering this field accelerates toward the sun, and its path bends. The shape of that bending depends on the body's incoming speed and direction. If the incoming energy relative to the sun is negative, the path is bound, and the curve is an ellipse. If the incoming energy is near zero, the path can be close to a parabola. If the incoming energy is positive, the path is a hyperbola. In all cases, the local motion is smooth and continuous. The object does not jump. It does not zigzag. It follows a conic section with the sun at one focus for bound cases, or with the sun at one focus for the hyperbola as well. This is the geometric expression of Newtonian gravity for two bodies. In the real solar system, other masses contribute. Planets pull. Their pulls are smaller, but can still be important, especially during close approaches. The most influential planet is often Jupiter. Saturn also matters. Earth's gravity does not usually alter the object's trajectory substantially unless the object passes close, but Earth's motion matters greatly because observations are made from Earth. This means that the observed path on the sky is not the same as the object's path in space. The observed path is the line of sight from Earth to the object projected onto the sky. That projection changes as Earth moves. Therefore, even a simple conic in space can appear as a more complicated curve on the sky. Still, it will remain smooth. The smoothness is one of the first signatures of gravitational motion. In orbit, fitting gravity's curve is represented by orbital elements. These elements include the shape parameter and the orientation of the orbit in space. They also include a parameter that sets where the object is on its orbit at a given time. When the orbit is being determined from early observations, these parameters are uncertain. Small changes in them can shift the predicted path noticeably. Yet the family of possible paths remains conic-like because the underlying equation is gravitational. This is why the object's track does not look random even before it is well known. Gravity already imposes a strong structure. Another way to see the same structure is to consider speed change. Gravity predicts that speed increases as the object approaches the sun. The object's angular motion on the sky can speed up as well, but that depends on distance. A close object can move quickly across the sky even if its linear speed is modest. A distant object can move slowly even if its linear speed is high. As distance is constrained, and as the object moves inward, observers can see changes in angular speed that match the gravitational expectation when combined with geometry. These changes further reinforce the sense of a non-random path, yet they also create opportunities for confusion. If early distance estimates are wrong, the expected angular speed may be wrong, and later measurements may appear to show that the object is accelerating in an unexpected way. In many cases, that impression disappears once the orbit is refined. Therefore, this section emphasizes that gravity provides the default explanation for smooth curvature and changing speed. Any claim that the path is structured must first be compared to this default. Another aspect of gravity's curve is the influence of the observer. Earth orbits the sun. This changes the observer's perspective. Parallax shifts the object's apparent position against background stars. Over weeks, parallax can be significant, especially for closer objects. For distant objects, parallax is smaller, but still measurable with precise astrometry. Parallax is a structured effect. It repeats annually for bound objects and appears as a component of the observed motion over the observation window. In early discovery phases, parallax can be the main driver of orbit tightening because it constrains distance. Therefore, the path on the sky may show subtle curvature that is partly due to Earth's motion rather than the object's own bending. This is still not random. It is another deterministic layer. The orbit fitting process includes Earth's motion and light travel time. Light travel time means the object is observed where it was when the light left it. For solar system distances, the delay can be minutes to hours. Including this delay matters when high precision is sought. Again, this is a structured correction. It makes predicted positions match observed positions better. It can create a small apparent timing shift if ignored. Therefore, careful modeling is part of maintaining the non-randomness. A poorly modeled effect can produce residual structure that might be misinterpreted as a force. A well-modeled effect reduces residuals and clarifies whether any force beyond gravity is needed. In a calm account, the gravitational curve is therefore not just a conceptual background. It is the baseline that must be exhausted before any other interpretation is considered. This baseline also explains why the path can be predicted. If one knows the orbit, one can forecast where the object will appear. The forecast includes uncertainties that shrink as data accumulates. The shrinking is again a structured effect. It reflects better constraint. As the uncertainty shrinks, the prediction becomes more precise. The object can be found with narrower searches. This is how follow-up observations are planned. It is also how an object's category can be determined, because bound and unbound orbits differ most clearly in the far field, and that far field must be inferred from the orbit. In the case of a potentially interstellar object, the gravitational curve becomes a diagnostic. If the orbit is hyperbolic, the object is unbound. The path is still a smooth conic. It is not random. It is simply open. This openness can be described as the object arriving from infinity and departing to infinity in the idealized two-body picture, with a constant hyperbolic excess speed far away. That excess speed is a parameter inferred from the orbit. It tells how fast the object is moving through the solar system, compared to a bound body at the same distance. Again, this is structure. It is a number derived from a curve. It does not imply purpose. It implies energy. The title suggests that the path does not look random, and in this gravitational section, that can be restated in a more precise way. The path is consistent with a solution to the equations of motion under gravity. It has smooth curvature, consistent speed evolution, and predictability within shrinking uncertainties. If later sections introduce residual structure beyond gravity, that structure will be small compared to this dominant curve. It will be a refinement, not a replacement. Therefore, before any deeper interpretation, it is worth lingering on how much of the apparent pattern is already accounted for by gravity and geometry. Most of it is. The remaining question is whether the residuals, once gravity and observer motion are modeled, still show a repeatable drift. That drift, if present, is the place where additional forces or measurement biases enter. But the path as a whole is already non-random in a fully sufficient way. It is the natural shape of motion in a gravitational field as seen from a moving Earth, and it is the foundation on which all later claims rest. From points to an orbit is a careful conversion of sightlines into a three-dimensional path. This section stays with that conversion because the feeling that the path does not look random often comes from watching an orbit solution sharpen and stabilize. The sharpening is real, but it is not a new physical behavior. It is a reduction in uncertainty. The raw observations are angular positions on the sky at specific times. Each observation is a line of sight from the observer to the object. A single line of sight gives direction, but not distance. With two lines of sight at different times, one can begin to infer motion, but distance remains ambiguous because many combinations of distance and velocity can project to the same angular shift. With multiple lines of sight over days, the ambiguity decreases because Earth's motion and the object's gravitational curvature introduce subtle changes that only certain distances can match. Orbit determination uses these constraints to estimate the object's state vector, its position and velocity in space at a reference time. From that state, the orbit can be propagated forward and backward under gravity to predict positions at all observation times. The differences between predicted and observed positions are residuals. The fitting adjusts the state until residuals are minimized. In practice, this is done through iterative algorithms. An initial guess is made often based on short arc methods that assume a simple motion. The guess is refined. Each refinement uses the sensitivity of predicted positions to changes in the state. As more observations are added, the sensitivity structure becomes better constrained. The result is that the orbit estimate converges and the predicted path becomes stable. This convergence is often what observers mean when they say the path is not random. It becomes a precise curve rather than a fuzzy guess. Yet it is important to recognize how fragile early orbits can be. In the earliest days, the observation arc may be only a few hours. In that regime, distance is poorly constrained. The orbit might be compatible with a near object on a bound orbit or a far object on a different orbit. If later observations reveal that the object is not where the early orbit predicted, this can feel like the object changed course. In reality, the early orbit was simply one member of a broad family of solutions. The family included the true orbit, but the early best fit might not have been close to it. When new data arrives, the best fit shifts. This shift is not randomness. It is learning. The correct way to express this is with uncertainty, ellipses, and covariance. An orbit solution is not just a set of elements. It is a distribution of possible orbits consistent with the data. The width of that distribution shrinks as the arc grows. The shrinking is itself structured. It often shrinks faster when observations are taken at geometries that provide strong parallax, such as when Earth's motion changes the line of sight significantly. It also shrinks when the object brightens and astrometric precision improves. Therefore, the quality of the orbit is tied to the brightness evolution and the observing campaign. This is another deterministic link. The orbit becomes less random-looking because the observational information content increases. Another reason early orbits can mislead is that different types of errors can mimic different orbital changes. A systematic astrometric bias in one direction can shift the inferred orbit elements. If this bias is present for the first several nights, and then absent later, the orbit solution can jump when the data set changes. Such a jump can be interpreted as a sudden acceleration or a change in behavior. In reality, it is a change in the data. This is why analysts often look at residuals by observatory and by time to detect systematic offsets. The weighting of observations matters as well. Some observations have smaller uncertainties and should count more. If weights are misassigned, low-quality data can pull the orbit. Later, when high-quality data dominates, the orbit shifts back. Again, this can look like the object is not following a predictable path when it is. The orbit is predictable. The estimate is the part that is shifting. A disciplined approach uses robust fitting and outlier rejection, but those methods also have pitfalls. If an outlier is actually a real deviation due to a non-gravitational force, rejecting it would hide the signal. If a measurement is biased but not extreme enough to be rejected, it can imprint a trend. Therefore, orbit determination is a balance between trusting data and questioning it. The outcome is judged by residual patterns and by stability. Another aspect of converting points to an orbit is the choice of reference frame. Observations are made from Earth, but orbits are often computed in a heliocentric frame or a barycentric frame. The barycentric frame centers on the solar system's center of mass and is useful for determining whether an orbit is truly unbound. The heliocentric frame centers on the Sun and is intuitive for understanding solar-driven forces. Transformations between frames are well defined, but if different analysts use different conventions, comparisons can become confusing. A path can appear to shift simply because different frames are being compared. This is not common in careful practice, but in public or informal summaries, it can contribute to the sense that the object's path is mysterious. The remedy is to keep the frame consistent and to specify it. The conversion from points to an orbit also includes non-gravitational terms when needed. In early stages, these terms are often not included because the data are insufficient to constrain them and because the simplest model is preferred. As more data arrives, analysts may test whether adding a small acceleration term improves the fit. If it does, the orbit solution changes. A gravity-only orbit might not match later positions, as well as an orbit with a small non-gravitational term. To a casual observer, this could look like the object's path is becoming more organized as a new term is added. In reality, the path was always organized. The model simply became more complete. Yet this process can create a subtle narrative trap. If a non-gravitational term is introduced too early, it can soak up modeling errors or systematic biases and produce a misleading coefficient. Later, when the data set improves, the coefficient may shrink or change sign. This can lead to the impression that the object's acceleration is erratic. The truth may be that the inference was premature. Therefore, the timing of introducing extra terms matters. The stable way to do it is to wait until the orbit is constrained well enough that additional parameters are meaningful and to test stability under different data subsets. This section also notes that orbit solutions are often reported and updated publicly as new data arrives. Each update can change the predicted ephemeris. Observers who follow these updates can see the predicted path shift. This shift can be interpreted emotionally as the object refusing to be pinned down. In reality, it is the normal refinement of a parameter estimate under uncertainty. The path in space is not changing. The estimate is converging. The correct way to read these updates is not as a story of a wandering object, but as a story of shrinking error bars. When the error bars shrink, the orbit becomes precise enough to support deeper questions, such as whether the orbit is unbound and whether residuals suggest non-gravitational forces. In that sense, the non-randomness becomes a tool rather than a claim. The orbit provides a coherent framework within which deviations can be measured. Without a good orbit, any talk of deviation is meaningless. Therefore, the conversion from points to an orbit is not a technical aside. It is the foundation that allows the later discriminations. It turns a sequence of faint detections into a known trajectory. It clarifies which apparent surprises are simply the collapse of ambiguity. It reveals whether residuals remain after ambiguity is removed. And it teaches a quiet lesson. A path that does not look random is often the product of careful inference rather than of surprising motion. And the most valuable moment is not when the curve looks smooth on a plot, but when the residuals become small enough and stable enough that any remaining structure is no longer a shadow of uncertainty, but a real clue about forces activity or measurement bias to be tested with the same patience that first turned scattered points into a curve. Testing for structure in residuals is where the phrase "not random" gains its sharpest meaning. This section stays with that test and treats residuals as a diagnostic layer that sits just inside the orbit itself. The orbit provides the dominant curve. Residuals describe what remains once that curve is subtracted from the data. If nothing remains except noise, then the path is fully accounted for by gravity and measurement uncertainty. If something remains and it repeats, then the remaining pattern is itself not random, and it must be explained either by a missing force or by a systematic bias in measurement. The first step in residual testing is simple visualization. Residuals are plotted versus time. If the residuals scatter symmetrically around zero and show no drift, that suggests the model is adequate. If the residuals drift, that suggests a systematic mismatch. The drift can be in right ascension, in declination, or along the track. Along-track residuals are especially suggestive of timing errors, which can come from a transverse acceleration or from an incorrect time of perihelion in the orbit solution. Radial residuals aligned with the sun direction can suggest radiation pressure or outgassing or coma-induced centroid shifts. Out-of-plane residuals can suggest a normal component, perhaps from a jet, or they can suggest a reference frame issue or a systematic bias in a subset of data. The direction is therefore a clue, but it is not decisive without further checks. The second step is to plot residuals versus solar distance. If residual magnitude increases as the object approaches the sun, that can suggest a solar-driven effect, such as outgassing radiation pressure or thermal recoil. If residuals show no dependence on distance, that can suggest a constant bias or a constant unmodeled acceleration over the interval. Yet this test can be misleading if the observation arc covers a limited distance range, or if the data quality changes with distance because the object becomes brighter and is measured more precisely. Improved precision can reveal smaller residuals that were previously hidden, which can make it look as though residuals appear only later. This is why residuals must be interpreted alongside measurement uncertainties and weights. The third step is to plot residuals versus observatory and instrument. Different telescopes have different systematic patterns. If one observatory's residuals are consistently offset in one direction, it may indicate a calibration bias. If the inferred acceleration is driven mainly by one observatory's data, it may be a systematic. If multiple independent observatories show the same residual drift, it is less likely to be an instrument-specific bias. This check is especially important for faint objects, where small systematic errors can dominate. A fourth step is to examine residuals versus viewing geometry. The solar elongation, the angle between the sun and the object as seen from Earth, affects background brightness and measurement conditions. The phase angle affects brightness and the scattering geometry of any dust. The position of the object relative to the Milky Way affects star crowding. If residuals increase in crowded fields, background contamination may be responsible. If residuals correlate with the sun direction on the detector, coma tails could be biasing centroids. These correlations can be tested by projecting residuals into a frame aligned with the sun object direction on the sky. If residuals consistently point away from the sun, coma bias or radiation pressure becomes a candidate. If residuals consistently point along the direction of motion transverse forces or timing offsets become candidates. Again, these are indications, not proofs. The fifth step is to use different reduction methods on the same raw images when possible. This is an important but often overlooked practice. If the object has a faint coma, centroid determination can depend on the fitting method. A simple centroid can be pulled by asymmetry. A point spread function fit can be more robust if the nucleus dominates. A coma model subtraction can further isolate the nucleus. If different methods yield different positions, the measurement is sensitive to coma and to background. If the acceleration signal disappears when nucleus-centered methods are used, then the signal was not a physical acceleration of the nucleus. It was a measurement artifact. If the signal persists across methods, it is more likely real. Another important step is to test the model complexity. If a constant non-gravitational acceleration term is added and residuals improve, one might be tempted to declare a force. But one must test whether the improvement is meaningful compared with the added degrees of freedom. One must also test whether the parameter is stable. Stability is tested by fitting over different time windows. If the acceleration parameter is similar across windows, it suggests a consistent physical effect. If it changes drastically, it suggests either a time-variable force or an unstable inference. Time-variable forces can occur in comets due to evolving activity, yet they can also occur due to changing coma geometry and centroid bias. Therefore, stability tests must be paired with imaging and photometry. If acceleration variability coincides with brightness changes or morphological changes, physical evolution becomes more plausible. If it coincides with changing observing conditions or data sources, systematic bias becomes more plausible. Residual testing also includes checking for the signature of outliers. A few bad measurements can create apparent trends if they are not recognized. Robust fitting methods reduce the influence of outliers, but they cannot remove coherent biases. Therefore, analysts often examine the distribution of residuals and identify clusters. If residuals show a heavy tail, outliers may be present. If residuals show a bimodal distribution by observatory, systematic offsets may be present. If residuals show periodicity, rotation-related centroid variations, or cadence-related biases may be present. Each pattern suggests a different diagnostic. In a calm narrative, this is the core idea. The question is not whether the path looks patterned. The question is whether the remaining mismatches after fitting the dominant pattern also look patterned, and if so, whether that remaining pattern aligns with known physical or observational causes. The phrase "following a path that does not look random" can therefore be translated into a disciplined workflow. First, fit gravity and observer geometry. Then examine residuals for structure. Then test whether the structure is robust to data selection, weighting, and reduction method. Then and only then interpret it physically. If the residual structure remains robust, the physical candidates are not exotic. They are the small forces already known to act on small bodies, outgassing radiation pressure and thermal recoil. Or they are the measurement biases that arise from dust coma and background contamination. A useful way to hold this is to remember that residuals are not a property of the object alone. They are a property of the object, plus the measurement process, plus the model. Therefore, a non-random residual pattern can originate in any of those components. The goal of residual testing is to localize the origin. Does the pattern track the sun direction, suggesting solar-driven forces or coma tails? Does it track the direction of motion, suggesting transverse acceleration or timing offsets? Does it track observatory, suggesting instrumental bias? Does it track field crowding, suggesting contamination? Does it track brightness changes, suggesting evolving activity? Each answer narrows the search. Over time, as more data is collected, the answers become sharper. In the end, a path that does not look random is expected, but a residual pattern that does not look random is the true signal of something beyond the simplest model. That something is often small and often ordinary. It becomes meaningful only when it remains after every ordinary way of fooling oneself has been checked. This is why residual testing is not a minor technical step. It is the boundary between the visible smoothness of an orbit plot and the deeper question of whether the object's motion contains a subtle extra drift that is itself deterministic, measurable, and interpretable, or whether the apparent drift is a shadow cast by how faint light is turned into positions. The interstellar question sits just inside the gravity curve because it is about whether the curve is open or closed. This section stays with bound versus unbound motion and explains why the conclusion is not a matter of impression. A path can look non-random and still be either bound or unbound. The distinction is made by energy. In a two-body picture with the Sun, a bound orbit has negative specific orbital energy. An unbound orbit has positive specific orbital energy. This energy is inferred from the fitted position and velocity of the object relative to the Sun. It is often expressed through eccentricity. Eccentricity less than 1 indicates a bound ellipse. Eccentricity greater than 1 indicates a hyperbola. Yet early in discovery, the observation arc is short and uncertainties are large. In that regime, an eccentricity slightly above 1 does not necessarily mean the object is interstellar. It can mean the orbit is not yet constrained. As more observations accumulate, the uncertainty in eccentricity shrinks. If the best fit remains above 1 by a margin that is large compared with uncertainty, the unbound nature becomes secure. Another quantity that becomes meaningful is the hyperbolic excess speed, the speed the object would have far from the Sun after removing the Sun's gravitational potential. For an unbound orbit, this speed is positive and can be inferred. For a bound orbit, it is not defined in the same way. A significant hyperbolic excess speed supports the interstellar interpretation because it indicates the object is not merely slightly unbound due to a recent planetary encounter. Still, one must be careful. A solar system object can be scattered onto a hyperbolic path by a close encounter with a planet, especially Jupiter. In that case, it is unbound now, but not interstellar in origin. To distinguish these cases, analysts examine the orbit on the incoming leg before any close planetary encounters. They often use a barycentric frame centered on the solar system's center of mass because it removes some of the short-term wobble due to planetary motion around the Sun. If the incoming barycentric orbit is hyperbolic, then the object is unbound before entering the planetary region, which supports interstellar origin. If the incoming orbit is bound and becomes unbound after an encounter, then the origin is solar system. For a truly interstellar visitor, the incoming direction and speed are properties of its motion through the galaxy, not of the solar system's scattering reservoirs. This is part of why the path can be called not random in a specific sense. It is a draw from a background distribution of interstellar trajectories. But it is still governed by gravity once it enters the Sun's influence. The interstellar conclusion therefore rests on careful orbit fitting and on propagating the orbit backward under gravity to see the incoming asymptote. That propagation includes uncertainties. Small uncertainties in velocity can lead to large uncertainties in inferred origin direction when traced far back. Therefore, even when an object is classified as interstellar, it is usually not possible to identify a particular parent star. The incoming direction can be compared to the motions of nearby stars, but the uncertainties and the dynamical complexity of the galaxy make a unique match unlikely. In a disciplined narrative, this is treated as a limitation rather than a mystery. The object's path is not random, but its origin is not usually traceable to a single source. The value lies in the fact that it is a sample from a broader population. Another part of the interstellar question is that the inference of non-gravitational acceleration can affect the classification if it is large enough. A small additional acceleration can bias the inferred eccentricity, especially if it acts over the observation arc. If an orbit is fit under gravity only, and the object actually experiences a small outgassing-driven push, the fitted orbit elements may shift. This could in principle push a marginal eccentricity estimate across the threshold of 1. Therefore, for objects near the boundary, analysts may test models that include non-gravitational terms to see whether the interstellar classification is robust. For a clear interstellar case, this is less of an issue because the eccentricity is well above 1. But the principle matters. Classification depends on the model, and the model depends on whether non-gravitational forces are present. This creates a subtle loop. One should not assume interstellar origin based on an early gravity-only orbit if later evidence suggests significant non-gravitational acceleration. Instead, one should refit with appropriate terms and examine whether the unbound nature persists. In most cases, where interstellar origin is claimed, it does persist, but the discipline remains. Another reason this section matters is that an interstellar path can invite pattern seeking. A particular incoming direction might look aligned with a certain part of the sky, and it might be described as not random in a suggestive way. Yet the sun's motion through the local interstellar environment creates a preferred direction for incoming interstellar objects in the heliocentric frame. The sun moves through the galaxy. Interstellar objects have their own velocities. The relative velocity distribution can produce an apparent clustering of incoming directions. This clustering would be a physical selection effect, not an intention. It would still be deterministic and still explainable. But it shows how easily the word random can be misused. A distribution can be non-uniform without requiring any special cause beyond relative motion and observational selection. Observational selection is also important. Surveys do not detect all directions equally. They observe some parts of the sky more often. They have limiting magnitudes that vary with sky brightness and with weather. They detect objects more readily when they are near Earth, when they are near opposition, and when they are in less crowded star fields. This selection can bias the set of discovered interstellar objects and make their incoming directions appear patterned. Again, the pattern is not necessarily in the universe. It can be in the survey strategy. Therefore, even the statement that an interstellar object's path does not look random must be treated carefully. The path is deterministic. The sample of paths we detect is selected. The final calm point of this section is that the interstellar classification, when it is robust, is a strong statement about dynamics. It says the object is not a long-term member of the solar system. It passes through once. This rarity does not make the path mysterious. It makes the observing window precious. It encourages careful measurement, longer arcs, and multiple methods, because there will not be a return. The non-randomness of the path remains grounded in gravity. The interstellar nature is an additional geometric property of that path. It is not a claim about behavior beyond physics. It is a claim about energy. And it sets up the next inward layer of the story if the object is interstellar, and if residuals show additional structure beyond gravity, then any small non-gravitational acceleration becomes especially important to understand because it can affect how the incoming and outgoing asymptotes are determined, and because it connects the object's physical nature to its motion in a way that can be tested within the limited time available. Direction matters, but it matters in a bounded way. This section stays with the incoming velocity vector and what can and cannot be traced back from it, because this is one of the places where the idea of a non-random path can be misunderstood. The incoming direction of an interstellar object is defined by the asymptote of its hyperbolic orbit. Far from the Sun, the object would move in a straight line with a constant velocity relative to the solar system barycenter. As it approaches, the Sun's gravity bends that line into a hyperbola. The incoming asymptote is the straight line the object would follow before the bending becomes significant. In orbit, fitting this direction is inferred from the solution and can be expressed as a point on the sky from which the object appears to come, sometimes called the radiant. It is tempting to imagine that this direction points back to a home star. In practice, it rarely does in a meaningful way. The galaxy is dynamic. Stars move relative to one another. Over millions of years, small uncertainties in velocity become large uncertainties in position. Even if the velocity were known perfectly, the object may have been ejected long ago from a system that has since moved far away. It may have been perturbed by other stars and by the galaxy's gravitational field. Therefore, tracing an incoming direction back to a specific origin is usually not possible. What can be done is more modest. The incoming direction can be compared statistically to known stellar motions and to the Sun's motion through the local environment. One can ask whether the direction is consistent with the local standard of rest, a reference frame tied to average stellar motion in the vicinity. One can ask whether the incoming speed relative to that frame is typical. These are population questions. They do not identify a home, but they can inform whether the object is kinematically unusual. A kinematically unusual object might have an unusually high speed relative to the local environment. That could suggest a different dynamical history, such as ejection from a system with strong gravitational interactions. But even then, it remains an inference about population, not a pinpoint origin. Another bounded use of direction is to examine whether the object's incoming trajectory aligns with regions of the sky where surveys are most sensitive. As mentioned, detection is not uniform. If surveys watch certain areas, more often more objects will be found coming from those directions, simply because those are the lines of sight along which objects are discovered. This can create apparent clustering of radiance. It can also create a sense that paths are not random when in fact the detected sample is shaped by observation strategy. Therefore, any statement about direction must be paired with an awareness of selection. Another bounded use of direction is to evaluate whether the motion is consistent with purely gravitational bending. If the orbit is fit and residuals show a systematic drift, the inferred incoming direction can change slightly when non-gravitational terms are included. This is important because the incoming direction is a derived quantity. It is not directly measured. It is computed from the best fit parameters. If those parameters change, the direction changes. Therefore, one should not treat an early incoming direction as fixed. It is part of a solution that can refine. The magnitude of change depends on how strong the non-gravitational terms are and on how long the arc is. For small accelerations over a short arc, the change may be negligible. For larger accelerations or longer arcs, it can matter. This again keeps the story grounded. The path does not look random because it is fitted by a model and derived quantities depend on that fit. Another way direction matters is in assessing the plausibility of non-gravitational forces. Sunlight-driven forces produce accelerations that have preferred directions relative to the Sun and relative to the orbit. Outgassing tends to be linked to the sunlit hemisphere, producing a force roughly away from the Sun with possible transverse components. Radiation pressure is away from the Sun. Thermal recoil depends on rotation and can produce along-track components. If the residual pattern implies a direction that is inconsistent with any solar-linked geometry, one might suspect that the signal is not physical or that the model is misspecified. Yet this is subtle because acceleration is inferred through parameterization in orbit-relative components. If the fit assumes the force can be decomposed into radial and transverse components, then it is already assuming a geometry tied to the Sun and orbit. A force fixed in inertial space would not be well captured and would likely produce unstable coefficients rather than a clean direction. Therefore, the most meaningful directional tests are those that compare the residuals and fitted components to the Sun direction on the sky and to the object's direction of motion. If residuals consistently point away from the Sun across independent data, it suggests either a solar-driven force or a sunward coma centroid bias. If residuals consistently point along the motion, it suggests either a transverse force or a timing offset due to orbit parameter uncertainty. If residuals rotate with changing geometry in a way consistent with solar linkage, it suggests a real solar-driven effect. If residuals stay fixed in detector coordinates or in observatory coordinates, it suggests an instrumental systematic. These are the practical ways direction enters. There is also the direction of the object's angular motion on the sky. This changes as Earth moves and as the object's trajectory bends. For a coherent orbit, this change is smooth. If observers perceive the path as non-random, they may be responding to this smooth change. Yet smooth change does not necessarily imply anything beyond gravity. It implies that the object is being tracked well enough that the expected curvature is visible. In that sense, direction is a marker of observational maturity. As the orbit becomes better known, the predicted direction of motion becomes more accurate. This helps observers plan exposures and track rates. It also helps link detections across nights. Again, this is structure. It is not a mystery. The final bounded point is about interpreting the phrase "does not look random" as it applies to interstellar origin. An interstellar object's incoming direction might look special simply because interstellar origin itself feels special. But from a physical standpoint, an interstellar object is a body moving through the galaxy that happens to pass through the solar system. The distribution of such passes is governed by relative velocities and by geometric cross-sections. The Sun's gravitational focusing increases the effective cross-section slightly. These factors can create non-uniformities in incoming directions in the heliocentric frame. Such non-uniformities are not surprising. They are expected outcomes of relative motion. Therefore, if the path's direction appears patterned, the first explanations are geometric and kinematic, not dramatic. The path is non-random because motion is governed by forces and because detection is shaped by selection. What is valuable is not the impression of pattern, but the quantifiable information in the direction and speed. Those quantities, when measured well, can place the object within a population. They can indicate whether its speed is typical or unusual. They can help estimate how many such objects might exist and how often they pass near the Sun. They can also constrain whether non-gravitational forces are altering the orbit enough to matter for the derived incoming direction. This is a disciplined use of direction. It keeps the story from drifting into suggestive language and keeps it anchored in what direction and speed truly provide a vector that summarizes the object's entry into the solar system, and a set of tests for whether the measured residuals and derived motion behave as they should under the simplest solar-driven forces and under careful measurement. Apparent patterns can be produced by the telescope before any physics beyond gravity is involved. This section stays with the measurement process because it is one of the most common sources of non-randomness in residuals. The sky is measured through instruments, and instruments have biases. A bias is not random. It repeats. If it repeats, it can be mistaken for a physical effect. For a faint moving object, the measurement chain begins with photons arriving at a detector. The detector records them as counts. The image is then processed. Background is subtracted. Stars are identified. The mapping between pixels and sky coordinates is computed. The moving object's position is estimated as a centroid. Each of these steps can introduce small systematic offsets. When those offsets repeat, they create structured residuals. A key source of structured offsets is the reference catalog. Modern star catalogs are very accurate, but they still have small regional systematics and magnitude-dependent biases. If the calibration stars used in a field have small systematic position errors, then the derived astrometry for the moving object will inherit those errors. This can produce a consistent offset in a particular region of the sky. As the object moves across the sky, the calibration field changes. The bias may change slowly. This can produce a drift in residuals that is tied to sky position rather than to physical forces. Because the drift is smooth, it can look like an acceleration. Another source is differential chromatic refraction in Earth's atmosphere. The atmosphere refracts light. The amount of refraction depends on wavelength. If the object's color differs from the average color of the reference stars, the refraction correction may not be perfect. At higher air mass near the horizon, this can produce systematic position shifts. These shifts are not random. They correlate with air mass and with observing time. If observations are often taken at similar air mass, the bias can repeat. This can create a structured residual that is mistaken for a physical drift. Another source is optical distortion in the telescope system. Wide-field survey telescopes have distortion across the field. Distortion models correct it, but models are not perfect. If the object is measured near the edge of the field more often than near the center, the distortion residuals can bias positions. If a particular survey uses a consistent pointing pattern, the object may fall in similar parts of the detector on successive nights. This can create a repeating bias. Again, it is non-random. A further source is background contamination. The object may pass near a star or a faint galaxy. If the background source is unresolved or faint, it can still pull the centroid. The centroid shift depends on the separation and brightness ratio. If the object passes through a crowded star field, such contamination becomes more likely. Star crowding is not random in a uniform sense. It correlates with galactic latitude and with the Milky Way. Therefore, residuals can show a pattern tied to where in the sky the object is. A signal that appears only in crowded regions is suspicious. A signal that appears in uncrowded regions as well is more likely physical. This is why residuals are sometimes plotted against star density. Another major source of bias for comet-like objects is a coma. Even if the coma is faint and unresolved, it can shift the centroid if it is asymmetric. Dust tails are pushed away from the sun. Therefore, the coma brightness distribution often has a sunward nucleus asymmetry and a tailward extension. If the centroid is measured without modeling the coma, it can be pulled tailward, which is roughly away from the sun. This produces a residual pattern aligned with the sun direction. Such a pattern could be interpreted as radiation pressure or outgassing pushing the nucleus outward. But if it is a centroid bias, the nucleus is not accelerating that way. The measured light distribution is. This is one of the most important confusions in comet astrometry. It is made worse by faintness. If the object is faint, observers may not detect the coma, yet it can still be present enough to bias the centroid. The solution is to compare the object's profile to stars and to use coma modeling if any extension is detected. Space-based imaging can help because it reduces seeing and can reveal subtle coma. Another clue is consistency across wavelengths. Dust scattering dominates in visible light. Thermal emission can dominate in infrared. If the measured position in infrared differs from the optical position, coma bias is indicated. Another bias arises from the object's motion during exposure. If the telescope tracks at sidereal rate stars are point-like and the moving object trails. The centroid of a trail depends on trailing and on how it is fitted. If the telescope tracks the object is point-like and stars trail. This can affect calibration. If different observations use different tracking modes, systematic differences can arise. For high precision, analysts must account for trailing and use consistent fitting methods. If not, residuals can show structure tied to exposure time and tracking rate. Again, it is a pattern that can be mistaken for physics. Timing errors also matter. Astrometric positions are tied to timestamps. If timestamps are wrong by even a small amount, the predicted position will be wrong because the object is moving. For fast-moving objects, a timing error of seconds can produce a position error. If an observatory has a systematic clock offset, its measurements will be systematically shifted along the direction of motion. This can create an along-track residual pattern that looks like a transverse acceleration. Because the clock offset is constant, the pattern is consistent. It is not random. The remedy is to verify timing systems and to cross-check against other observatories. Another subtle issue is the transformation between coordinate systems. Observations are sometimes reported in different astrometric standards, and conversions are applied. If a conversion is misapplied, systematic offsets can result. This is rare in professional pipelines, but can occur in heterogeneous datasets. The main point is that many non-random patterns can appear in residuals without any unusual forces. Therefore, the claim that a path does not look random must be paired with a careful statement about what part of the path is being discussed. The overall orbit is non-random by gravity. Residual patterns can be non-random either because of small forces or because of measurement biases. Separating these requires specific checks. One check is independence. If the same residual pattern is seen in data from multiple independent observatories with different instruments and reductions, instrumental bias is less likely. Another check is correlation with observing conditions. If residuals correlate with air mass, sky brightness, star density, or detector position, bias is likely. Another check is morphological evidence. If imaging shows coma or tail centroid bias is plausible. Another check is consistency with physical geometry. If residual direction aligns with the sun direction and increases with sunlight, solar-driven forces are plausible. But if residual direction aligns with the sun direction only when coma is present, coma bias is plausible. Another check is stability under re-reduction. If reprocessing images with coma modeling changes positions significantly, the earlier positions were biased. If reprocessing leaves positions unchanged, the bias is smaller. This section emphasizes that these checks are not optional details. They are the core of credible inference. A dramatic statement that an object's path is patterned could be nothing more than the repeating signature of a single survey's distortion model. It could be nothing more than a consistent clock offset. It could be the tail pulling the centroid. It could be a real non-gravitational push. The only way to tell is to treat the measurement as a system and to test where the pattern originates. In a calm view, this is not skepticism for its own sake. It is respect for the difficulty of measuring faint moving points with arc-second precision. It is the reason that early claims about subtle accelerations often soften or sharpen as the data set is cleaned. The sky's true motion is one thing. The recorded motion is another. When the two are aligned through careful calibration, the remaining non-randomness, if any, becomes meaningful. Until then, the telescope itself is an active participant in the pattern, and the first task is to measure the measurement. If the path drifts beyond gravity, the drift is introduced first as a term in a model, not as a dramatic claim. This section stays with that modeling step because it is the formal way to express a non-random residual pattern after measurement biases have been considered. The baseline model is gravity from the sun and planets, plus the observer's motion and light travel time. Once that baseline is in place, residuals are examined. If a coherent drift remains, analysts may add a non-gravitational acceleration term to the equations of motion. This term is small. It is often expressed in components relative to the sun and the orbit. One component points along the sun object line called radial. One component points along the direction of motion called transverse. One component points perpendicular to the orbital plane called normal. These components provide a convenient language because common physical mechanisms have preferred directions. Sunlight pressure is radial outward. Outgassing often has a strong radial component and can have transverse and normal components depending on thermal lag and jet geometry. Thermal recoil can produce transverse components depending on rotation. When the term is added, the fitting process solves for its magnitude, along with the orbital elements. The question is whether the term improves the fit in a stable, meaningful way. An improvement alone is not enough, because adding parameters always improves a fit to some extent. The improvement must be large compared to what would be expected by chance, given the measurement uncertainties. The fitted acceleration components must also be stable as more data is added. Stability is essential because a spurious signal caused by systematics or by a few outliers tends to shift when the data set changes. A real physical signal tends to persist and converge toward a stable value, or it varies in a way that can be linked to physical changes, such as increasing solar heating or evolving activity. The modeling step, therefore, includes multiple tests. One test is to fit the data with gravity only and examine residual structure. Another test is to fit with the added acceleration term and see whether residuals become more random. Another test is to fit different subsets of data. If the term is real, it should appear in subsets as well within uncertainty. Another test is to compare different observatories. If the term is driven by one observatory's systematic bias, it may vanish when that observatory's data is removed. Another test is to fit over successive time windows to see whether the term is constant or changing. The modeling step also requires a choice of functional form. One can fit constant acceleration components over the observed interval. This is a simple approximation that can be useful if the observation span is short and if the force is expected to vary slowly. For comet outgassing, however, forces often vary with solar distance. Therefore, another approach is to use a distance-dependent function that approximates how sublimation changes with distance. Historically, functions tuned to water ice have been used for many comets. For objects far from the Sun, other volatiles may be relevant, and the functional form may differ. Using an inappropriate function can create misleading coefficients. A constant term can also be misleading if the true force varies, because it will represent an average and leave structured residuals. Therefore, choosing the model is part of the inference. It is not neutral. Analysts must choose a model that is justified by the data and by the expected physics. When data are sparse, simpler models are preferred. When data are rich, more detailed models can be justified. This can create an evolving narrative. Early fits may suggest one magnitude of acceleration under a simple model. Later fits may refine it under a better model. This refinement can look like a changing behavior, but it may be a changing model. Therefore, reports of acceleration should be interpreted in the context of model choices. Another subtle point is that the added acceleration term can absorb some kinds of measurement bias. If the measured positions are biased away from the nucleus by a coma, the fit may add a radial acceleration term that improves residuals. The fit would then interpret the biased positions as nucleus motion. This is why the modeling step cannot substitute for careful measurement correction. The acceleration term should be introduced only after reasonable steps are taken to ensure that the astrometry tracks the nucleus and that systematics are minimized. If that is not possible, the interpretation of the term must remain cautious. It would be better described as an effective acceleration of the observed photocenter rather than a physical acceleration of the nucleus. That distinction matters. The phrase "following a path that does not look random" can be built into this modeling framework in a precise way. The path is non-random because it is captured by an orbit model. If residuals remain, their structure is non-random if it is repeatable and coherent. The added acceleration term is the formal way to describe that coherence. It compresses the residual pattern into a small set of parameters. Those parameters can then be compared to physical expectations. For example, if the fitted radial component is positive and grows as the object approaches the Sun, it is consistent with solar-driven forces. If the fitted transverse component is significant, it suggests thermal lag or rotation effects. If the normal component is significant, it suggests out-of-plane jets or complex geometry. But before interpretation, the parameters must be stable and robust. A model that yields wildly different components depending on which nights are included is not yet describing a real force. It is describing instability. Instability can arise because the data are insufficient or because systematics dominate. Therefore, the modeling step includes the discipline of waiting for convergence. Convergence is not a delay for its own sake. It is the condition under which small forces become separable from noise. Another part of this section is the scale. The non-gravitational accelerations typically considered in small body dynamics are tiny compared to solar gravity at the same distance. Solar gravity sets the main curve. The added term nudges it. Over many days, that nudge becomes a measurable shift in position. This is the sense in which a small drift can be detected. It is also why it can be easy to overinterpret early results. When the signal is small, it is close to the noise level. Therefore, multiple checks are required. In a calm account, the presence of a modeled non-gravitational acceleration is not a crisis. It is common for comets. Many comets require such terms to predict their positions accurately because outgassing is real. The interesting part for an interstellar object would be whether the magnitude and direction are consistent with plausible outgassing or sunlight forces given the object's observed properties. But that is a later layer. Here, the modeling step is simply the formalization of a non-random residual pattern into parameters that can be tested. It is the bridge between a qualitative impression of drift and a quantitative statement that can be checked against new data. Without that formalization, the phrase "does not look random" remains vague. With it, the phrase becomes a structured claim the data require an orbit, plus a small additional acceleration term, and the term has a measured direction, magnitude, uncertainty, and stability that can be interrogated. That is the point at which the story becomes scientific rather than suggestive, because it becomes possible to say not only that the path looks patterned, but exactly how and by how much and under what assumptions and with what remaining uncertainty. Outgassing is the first physical cause to test when a small drift beyond gravity is robust, because it is the most common way a small icy body departs slightly from a purely gravitational path. This section stays with outgassing as a conservative mechanism that can turn a path into something that looks less random than gravity alone would suggest in its residuals. The mechanism begins with sunlight. Sunlight warms the surface. If volatile material is present near enough to the surface, it can sublimate, shifting from solid to gas. The gas expands into space. As it leaves, it carries momentum. The nucleus experiences recoil in the opposite direction. That recoil is a force. Dividing by mass gives acceleration. Over time, that acceleration produces a systematic shift in the predicted positions. In orbit fitting, it appears as a non-gravitational term often correlated with solar distance and with the sun direction. The details depend on the geometry of emission. If emission is strongest on the day side, the force tends to point away from the sun. If emission peaks after local noon due to thermal lag, a transverse component can appear, pushing the object slightly along its direction of motion. If emission is concentrated in a jet that is tilted out of the orbital plane, a normal component can appear. This is the physical reason that outgassing can produce non-random residual patterns. The residuals are not random because the force is not random. It is tied to sunlight and to the object's rotation and surface structure. Outgassing is also variable. As the object approaches the sun, solar heating increases. For a given volatile, the sublimation rate often increases sharply with temperature, which increases as distance decreases. Therefore, outgassing-driven acceleration often strengthens on approach. Yet the relationship can be complex because different volatiles become active at different temperatures and because surface layers can insulate or crack. For an interstellar object, composition and surface structure are uncertain, but the basic physics remains. If volatile material is present and can escape, outgassing can occur. The next question is whether it can occur without obvious visual signs. Many people associate outgassing with a bright coma and a tail. That association is often correct for active comets near the sun, but it can be misleading for faint objects or for objects with gas-rich, dust-poor activity. Gas can be difficult to detect in broadband images. Dust is easier because it scatters sunlight efficiently. But dust lifting requires that gas flux is strong enough to entrain grains and overcome surface cohesion. If the gas flux is low or if the surface is cohesive, gas can escape with little dust. In that case, the object can experience recoil with minimal visible coma. In addition, if the nucleus is small, even a modest gas production rate can produce a measurable acceleration because the mass is low. This scaling is important. A small body can be pushed more easily. Therefore, the absence of a dramatic coma does not rule out outgassing. It only sets limits that must be compared to the required thrust. That comparison requires translating acceleration into momentum flux. The momentum flux needed is mass times acceleration. Mass depends on size and density. Size is often uncertain because brightness depends on reflectivity and on any dust. Density is uncertain because small bodies can be porous. Therefore, the required momentum flux can vary widely depending on assumptions. In a disciplined account, one explores plausible ranges rather than a single value. If within plausible ranges, modest outgassing can supply the required momentum, then outgassing remains a sufficient explanation. The next part of testing outgassing is spectroscopy. Gas species can be detected through emission lines or bands, or through infrared features. In the optical comets often show signatures from radicals produced by sunlight breaking apart parent molecules. In the infrared, parent molecules can be targeted more directly. The relevant species at large distances may include carbon monoxide and carbon dioxide, which can drive activity when water ice remains mostly stable. If spectroscopy detects such species, outgassing becomes supported. If spectroscopy does not detect them, it places limits on production rates. Those limits can be compared to the required thrust. If limits are low and acceleration is high, outgassing is strained. If limits are not low enough to rule out the required production, outgassing remains plausible. Imaging also contributes. A faint coma can be detected by comparing the object's profile to stars. A tail direction relative to the sun can indicate dust. A changing morphology can indicate jets. A stable sunward or tailward asymmetry can bias astrometry, which is a separate issue, but it also indicates activity. Photometry can show brightness changes beyond what distance alone predicts. These changes can indicate evolving activity. Light curves can reveal rotation, which affects how outgassing averages. If a rotation period is measured, and if the acceleration appears stable, it suggests a stable active region and stable spin state. If the light curve suggests tumbling or evolving spin, then outgassing forces may be variable, and a constant acceleration model may be inadequate. In such a case, residual patterns could appear complex, not because forces are exotic, but because the object's orientation and activity change. The energy budget provides a conservative check. Outgassing requires energy to sublimate material. Sunlight supplies that energy. The maximum sublimation rate is limited by absorbed solar power divided by the latent heat of sublimation. If a required mass loss rate exceeds what sunlight can supply at the object's distance, outgassing is implausible, unless another energy source exists, which is not assumed here. This energy bound is useful because it does not depend on detailed chemistry. It depends on distance, cross-sectional area, and albedo. Yet it still depends on size and albedo, which must be constrained. Therefore, outgassing tests are tied to size tests. Thermal infrared observations that constrain size and albedo are especially valuable. If the object is large and dark, it absorbs more sunlight and could support more outgassing. If it is large and bright, it absorbs less. If it is small, it absorbs less but needs less thrust. These scalings must be considered together. Outgassing also creates torques. Jets can spin the object up or down. Observed changes in rotation period can support active torques and therefore outgassing. Fragmentation and mass shedding can also support activity. If the object brightens unexpectedly and shows signs of fragmentation, outgassing becomes more plausible. Yet these same signs can also create centroid biases. Therefore, in testing outgassing, one must keep separate the dynamical effect on the nucleus and the observational effect on measured position. The conservative way to do this is to seek nucleus-centered astrometry and to compare it to photometry and morphology. If the inferred acceleration persists in nucleus-centered astrometry, and if activity indicators are present, the case for outgassing strengthens. If the acceleration persists, but no activity indicators are found under strong limits, the case weakens, and other mechanisms become more important. The phrase "following a path that does not look random" can then be reframed. The path is gravity plus a small drift. Outgassing is one of the ways that drift can be tied to sunlight and rotation, producing a repeatable, non-random residual signature. It is also one of the ways an interstellar object can reveal its physical nature through motion. If outgassing is present, the object is not just a passive traveler. It is reacting to sunlight with gas release. That reaction leaves a fingerprint in the orbit. But the fingerprint is only meaningful if the measurement process has been cleaned of coma biases and if the inferred acceleration is robust. Outgassing remains the first conservative hypothesis because it is common, physically grounded, and testable through spectroscopy, imaging, photometry, and energy constraints. It does not require unusual assumptions. It requires only that some volatile material is accessible in an interstellar object that is plausible. The remaining work is to determine whether it is necessary and sufficient in this case, and that work is done by turning the impression of a non-random drift into measured acceleration components, and then checking whether those components can be supplied by plausible gas recoil under the object's constrained size, mass, and observed activity. Light and heat are always present and can add small but coherent pushes. This section stays with radiation pressure and thermal recoil as conservative alternatives or complements to outgassing when residual patterns beyond gravity are robust. The key idea is that sunlight is not only energy, it is momentum. Photons carry momentum. When they strike a surface and are absorbed or reflected, they transfer momentum. This creates radiation pressure, a force directed away from the sun. The magnitude depends on the solar flux at the object's distance and on the object's cross-sectional area and reflectivity. The acceleration produced depends on the area-to-mass ratio. For a large, dense body, the area-to-mass ratio is low and radiation pressure is negligible. For a small or low-density body, the area-to-mass ratio is higher, and radiation pressure can produce a measurable acceleration. The direction is a strong constraint. Radiation pressure is primarily radial away from the sun. Therefore, if the inferred non-gravitational acceleration has a strong radial outward component and little transverse component, radiation pressure becomes more plausible. If the inferred acceleration is mostly transverse, radiation pressure alone is less likely. Another important fact is that both solar gravity and radiation pressure fall with distance squared. This means the fraction of gravity countered by radiation pressure depends mainly on physical properties, not strongly on distance. Therefore, if an object shows a significant deviation, radiation pressure can explain it only if the object has a high area-to-mass ratio, which implies small size, low density, or an unusual shape that presents large area for its mass. In conservative terms, small fragments and porous aggregates can have higher area-to-mass ratios than compact nuclei. Yet the required ratio can be bounded once size is constrained. Thermal infrared observations that estimate size are especially valuable here. If size is large, radiation pressure becomes too weak. If size is small, radiation pressure remains plausible. The second mechanism, thermal recoil, is driven by heat emission rather than by direct photon pressure. The object absorbs sunlight and later emits that energy as infrared radiation. Infrared photons carry momentum. If emission is anisotropic, the object experiences recoil. Anisotropy arises because the surface does not heat and cool instantly. Thermal inertia causes a lag. The warmest region can be displaced from the subsolar point, often toward the afternoon side for a rotating body. This creates a recoil that can have a transverse component along the direction of motion. This is the essence of thermal recoil effects, such as the Yarkovsky effect. For a small interstellar object observed over months, a thermal recoil could in principle create a measurable along-track drift if the object is small enough and the astrometry is precise enough. Like radiation pressure, thermal recoil is bounded by energy. The recoil force cannot exceed the total momentum carried by emitted thermal radiation, which is the emitted power divided by the speed of light. The emitted power is tied to absorbed solar power. Therefore, there is a maximum possible recoil. The actual recoil is some fraction of that maximum, depending on how directional the emission is. Real emission is not perfectly directional, so the net force is typically small. This places a strong bound. If an inferred acceleration requires a thermal recoil force near the maximum, it is implausible. If it is well below, it remains plausible. Thermal recoil also depends on rotation period and thermal properties. A slow rotator with low thermal conductivity can have strong day-night contrasts and significant lag, potentially producing larger recoil. A fast rotator or a highly conductive surface tends to reduce temperature gradients and reduce net recoil. Therefore, light curve measurements that infer rotation period become an important constraint. Thermal infrared observations can also hint at thermal inertia. A dusty surface often has low thermal inertia. A bare rocky surface has higher. The presence of a dust mantle can therefore influence recoil. Another nuance is that both radiation pressure and thermal recoil can be confounded by coma and dust. Dust grains are strongly affected by radiation pressure. If a dust tail forms, the brightness distribution can shift away from the nucleus. Astrometry that measures the centroid can then appear to show an outward acceleration, even if the nucleus is not pushed strongly. This is an observational effect, not a nucleus force. Therefore, when radiation pressure is considered, one must separate nucleus radiation pressure from dust radiation pressure. Nucleus radiation pressure depends on nucleus size and mass. Dust radiation pressure shapes the coma and tail and can bias positions. The two can produce similar residual directions. This is why nucleus-centered astrometry is essential. Thermal recoil is less directly confounded by dust, but dust can change thermal properties and can alter the apparent size and brightness, which affects inferences. Therefore, these mechanisms must be tested in a framework that includes morphology and size constraints. In the narrative of a path that does not look random, radiation pressure and thermal recoil offer a clean interpretation for a coherent residual drift that is tightly linked to the Sun. They are deterministic. They are not random. They would create residual structure that correlates with the Sun direction and with solar flux, yet they have distinct signatures. Radiation pressure is radial and requires high area-to-mass ratio. Thermal recoil can produce transverse components and depends on rotation and thermal lag. Outgassing can produce both radial and transverse components, and often produces observable gas and dust. Therefore, if residuals show a radial outward drift and no gas is detected, and the object is small, radiation pressure becomes a strong candidate. If residuals show a transverse drift, and the object's rotation and thermal properties support a lag, thermal recoil becomes a candidate. If residuals show complex components and activity indicators are present, outgassing is likely. The tests that decide among these candidates are observational. First, constrain size through thermal infrared. Second, measure rotation through light curves. Third, detect or limit gas and dust through spectroscopy and deep imaging. Fourth, ensure astrometry is nucleus-centered. Fifth, examine distance dependence of the drift. Sixth, examine direction relative to the sun and motion. A robust interpretation will satisfy multiple constraints simultaneously. If it does, the non-randomness of the residual drift becomes a physical fingerprint rather than an artifact. If it does not, the drift may be an artifact of measurement or a sign that the model is incomplete. The conservative virtue of radiation pressure and thermal recoil is that they do not require volatiles. They are present for any body exposed to sunlight. Therefore, they remain available explanations when outgassing is not detected. But they are not unlimited. Their magnitudes are bounded. Radiation pressure needs high area-to-mass ratio. Thermal recoil needs suitable rotation and thermal inertia, and still remains small for large bodies. These bounds prevent them from being catch-all solutions. They also allow strong statements when constraints are tight. If size is large and yet a large radial acceleration is inferred, radiation pressure is ruled out. If the inferred transverse acceleration would require a thermal recoil exceeding energy bounds, thermal recoil is ruled out. In that case, one returns to outgassing or to measurement biases. The story remains conservative because it stays within these known forces and within the measured constraints. The phrase "path does not look random" can therefore be completed in a disciplined way. The object follows a gravitational curve. If a repeatable drift remains, it can often be accounted for by one of the small sunlight-driven forces or by gas recoil, provided the object's size, mass, and activity state allow it. The task is not to seek mystery. It is to assign the correct small force, or to identify the measurement bias using the same patience that first turned scattered detections into a coherent orbit. Dust can mimic motion, and this section stays with that mimicry because it is one of the most direct ways a non-random residual pattern can appear without a corresponding non-gravitational force on the nucleus. The key is that telescopes measure light, and light is not anchored to the nucleus if dust surrounds it. Dust is a population of grains with a range of sizes. Once emitted, each grain follows its own trajectory under solar gravity and radiation pressure. Small grains are pushed more strongly by radiation pressure, so they accelerate away from the sun and can form a tail. Larger grains are less affected and tend to stay closer to the nucleus. The brightness of the coma and tail depends on the total scattering area of these grains, which can be large even for a small mass of dust, because many small grains have a large combined surface area. This is why a modest dust production can change an object's appearance and photometry significantly. For astrometry, the crucial point is that the brightness distribution becomes asymmetric. A symmetric brightness distribution centered on the nucleus yields a centroid that coincides with the nucleus. An asymmetric distribution shifts the centroid away from the nucleus. If the shift is stable and repeats, it creates a non-random offset in measured positions. Orbit fitting interprets that offset as a deviation from the predicted nucleus position. If the offset changes systematically with time, orbit fitting can interpret it as an acceleration. The direction of the offset often aligns with the sun direction because dust tails are shaped by radiation pressure away from the sun. Therefore, centroid bias can produce an apparent radial acceleration that is easy to confuse with radiation pressure or outgassing acting on the nucleus. The mimicry can be subtle. The coma may be too faint to be seen as an extended halo in typical images. Atmospheric seeing smears light into a point spread function that is already broad. A faint coma can be hidden within that blur. Yet even if the coma is not visibly extended, it can still bias the centroid because the centroid is sensitive to small asymmetries. This is especially true when the object is faint and the signal-to-noise ratio is low, because noise interacts with asymmetry in nonlinear ways. Therefore, a faint, unresolved coma can still create a coherent astrometric bias. This can be mistaken for a physical acceleration unless nucleus-centered methods are used. Nucleus-centered methods attempt to estimate where the nucleus is within the coma. One approach is to model the coma as a smooth radial profile, plus a point-like nucleus, and fit both. Another is to use high-resolution imaging to resolve the central condensation. Another is to use infrared observations, where the nucleus thermal emission contributes more relative to dust scattering. These methods can reduce bias. If the inferred acceleration disappears when such methods are used, the acceleration was not a nucleus force. It was a dust-induced photocenter drift. Another way dust can mimic motion is through time-variable dust production. If dust production increases as the object approaches the sun, the coma brightness increases. If the coma asymmetry increases, the centroid offset can grow. This can create a residual pattern that increases with time, resembling an acceleration that strengthens with solar heating. That is exactly the kind of signature one might otherwise attribute to outgassing. Therefore, dust mimicry can be particularly persuasive. It can create the right qualitative correlation with distance. But the difference is that the nucleus is not necessarily experiencing a corresponding increase in thrust. The dust is simply contributing more light and shifting the centroid more. This again shows why astrometry cannot be interpreted in isolation. It must be paired with imaging and photometry. If brightness changes and morphology changes occur at the same times, the inferred acceleration changes. The possibility of photocenter bias must be considered. Dust grain dynamics provide further structure. Dust tails are not straight. They curve. The curvature depends on grain sizes and on the object's motion. The tail direction relative to the sun and to the orbit changes with time. Therefore, the direction of centroid bias can also change. If the inferred acceleration direction follows the expected tail direction, changes that suggests dust bias rather than a stable nucleus force. A stable nucleus force tied to sunlight might remain more consistently radial. A dust tail can swing with geometry. This provides a test. Analysts can model dust tails using syndyne and synchrone frameworks that predict where dust of different sizes and emission times should be. Comparing those predictions to observed morphology can help estimate how the brightness distribution should shift. If the predicted shift matches the residual's dust bias, becomes a strong explanation. Another dust-related effect is fragmentation into a cloud. If the nucleus breaks into multiple pieces, the brightness may be dominated by a cluster of fragments and dust. The measured centroid can drift as the fragments separate and as dust is pushed. This drift can be smooth if the separation is smooth. It can mimic a continuous acceleration. Again, the cure is resolution. If imaging can resolve fragments, the motion of the nucleus can be tracked separately. If it cannot, the centroid represents the whole cluster. Orbit fitting that uses the centroid will then produce an orbit for the cluster, not necessarily for any single nucleus. This can produce apparent anomalies. Another layer is that dust and gas are often linked. Outgassing produces dust emission. Therefore, the presence of dust suggests that outgassing may be occurring. This can make interpretation tricky because outgassing can cause real nucleus acceleration, and dust can cause apparent photocenter acceleration in the same direction. The two effects can add or one can dominate. Disentangling them requires independent evidence of gas production and careful nucleus-centered astrometry. If gas is detected and dust is detected, outgassing is likely. But the magnitude of nucleus thrust versus photocenter bias still must be assessed. If gas is detected and the measured acceleration is consistent with expected thrust, nucleus acceleration can be real. If gas is not detected and dust is present, photocenter bias becomes more likely. Yet non-detection of gas is not definitive if the dominant gas is hard to detect. Therefore, the strongest cases come from combining multiple lines. Another practical way dust is assessed is by comparing the object's brightness to what would be expected from a bare nucleus of a given size. If brightness is higher than expected, dust may contribute. But this again depends on albedo and phase function. Still, sudden brightening events are suggestive. A sudden brightening can indicate an outburst or fragmentation, which often produces dust. If an acceleration signal appears around the same time, it may be due to changing photocenter. Therefore, time series matter. The story of a non-random path can shift here into a more precise statement. The orbit solution may show a drift. The drift may look patterned. But before it is interpreted as a force, one must ask whether the positions being fitted are positions of the nucleus or positions of the light centroid of dust. Dust can produce a pattern because dust dynamics are deterministic under sunlight and gravity. The pattern is real in the light, but it is not necessarily a force on the nucleus. In a calm documentary voice, this is not a complication to be avoided. It is the natural consequence of observing small bodies. Comets are not rigid point masses. They are sources of material. The material responds to sunlight. The resulting cloud can bias what is measured. Therefore, the measurement of motion becomes a coupled problem of dynamics and radiative transfer and instrumental response. The practical response is to treat astrometry and morphology as a pair. Deep images are used not only to detect dust, but to model its distribution. If dust is detected, astrometric reduction can be adjusted to estimate nucleus position. If dust is not detected to strong limits, photocenter bias is reduced, and a measured drift becomes more likely to reflect a real nucleus acceleration. In either case, the phrase "does not look random" remains accurate in a refined sense. The path in the images is not random because dust and nuclei both follow laws. The key is to ensure that when the orbit is interpreted as physics of the nucleus, the measurement is actually tracking the nucleus and not the drifting glow of dust. Rotation turns forces into averages and can also turn measurements into patterns. This section stays with spin and shape because they are the inward levers that determine whether a small drift beyond gravity is steady variable or only apparent. Rotation affects outgassing because it determines how long an active region faces the sun and how the jet direction sweeps through space. Rotation affects thermal recoil because it sets the phase lag between absorption and emission. Rotation affects radiation pressure because it changes projected area. Rotation affects dust bias because it can produce periodic asymmetries in coma structure. Therefore, when residuals show non-random structure, rotation is one of the first internal properties to examine. A light curve is the main observational window into rotation. If the object's brightness rises and falls periodically, rotation is implicated. The period of the light curve gives the rotation period, or a related period depending on symmetry. The amplitude gives clues about shape elongation and surface contrast. A large amplitude can indicate a strongly elongated shape. It can also indicate strong albedo variation. For a small body without dust, these are the main causes. For a dusty body, the light curve can be contaminated by coma variability, making interpretation harder. Still, if a clean periodicity is found, it can anchor models of forces. Outgassing forces depend on where the active region is. If there is a single dominant active region, the thrust direction in the body frame is roughly fixed, but in inertial space it rotates with the body. Over one rotation, the thrust can average out unless the activity is modulated by sunlight, such that it is stronger when the region is near local afternoon, and weaker when it is in darkness. Thermal lag naturally creates such modulation. If the net thrust after averaging is non-zero, it will have a direction tied to the spin axis and to the orbit. If the rotation is fast, averaging is strong, and the net thrust may be smaller and steadier. If rotation is slow, the thrust can be more intermittent and can produce more variable residuals. If the body tumbles, meaning it rotates around more than one axis, the thrust direction can vary in a complex way, producing irregular residual patterns that are still deterministic, but harder to fit with a simple, constant acceleration model. Such irregularity can look like randomness, but it is not random. It is a superposition of rotation states and variable solar illumination. Therefore, when residuals show complex structure, one possibility is that the object is tumbling, or that its spin axis is changing due to torques. Torques arise naturally from outgassing jets. A jet exerts force at a lever arm relative to the center of mass producing torque. Over time, torque can spin the object up or down and can change its axis orientation. This can change the direction of net thrust, changing residual patterns. Changes in rotation period inferred from light curves can support this. If the period shortens, the object is spinning up. If it lengthens, it is spinning down. Rapid changes would suggest strong torques, and thus significant outgassing or mass shedding. Thermal recoil forces also depend on rotation, but in a different way. Thermal recoil is strongest when the warmest region is displaced from the subsolar point. That displacement depends on thermal inertia and rotation period. If thermal inertia is low and rotation is moderate, the displacement can be significant, producing a net recoil that can have a transverse component. If rotation is too fast, the surface temperature becomes more uniform and the displacement diminishes. If rotation is too slow, the warm region may be closer to the subsolar point, producing a more radial recoil. Therefore, the sign and magnitude of thermal recoil depend on rotation and material properties. Light curve-derived rotation periods combined with thermal infrared-derived sizes and temperatures can constrain whether thermal recoil could be significant. Radiation pressure depends on area-to-mass ratio and on projected area. For an elongated object, projected area varies with rotation phase. This produces brightness variation and also can produce small variations in radiation pressure. These variations typically average out, but if the spin axis is oriented such that the object presents a larger area to the Sun on average, the net radiation pressure can be larger than for an average orientation. Still, the main determinant remains size and mass. Rotation contributes refinement. Rotation also affects measurement. If the object has a coma, the coma can respond to changes in illumination as the object rotates. Jets can turn on and off as active regions rotate into sunlight. The coma's brightness distribution can therefore be periodic. This can shift the centroid periodically. Such periodic centroid shifts can create residual patterns that repeat with the rotation period. An analyst might see a periodic residual and consider it evidence of a physical acceleration. In reality, it could be a periodic measurement bias. The way to test this is to compare residual periodicity with photometric periodicity and with morphological changes. If both share a period, coma-driven bias is plausible. If residual periodicity occurs without corresponding brightness, periodicity, other causes must be considered. Yet even then, the periodicity could be subtle or hidden by noise. Therefore, careful time series and multi-wavelength observations are valuable. Another internal property is shape and surface topography. Irregular shapes can create self-shadowing. An active region in a pit may receive sunlight only at certain angles, producing episodic outgassing. Pits can also collimate jets, increasing thrust efficiency in a particular direction. Collimation can increase net thrust because it reduces cancellation. This can produce a more coherent drift. It can also produce asymmetric coma structures. Therefore, a body with pits and jets can produce residual patterns that are both non-random and physically meaningful. Yet without resolved imaging shape remains inferred from light curves. The amplitude and waveform of the light curve can provide constraints. A smooth, double-peaked light curve suggests an elongated shape. A more complex light curve suggests irregularity or albedo patches. If the light curve is stable, the spin state is likely stable. If the light curve changes, the spin state or the coma contribution may be changing. The stability or variability of the light curve can therefore be compared to the stability or variability of the inferred acceleration parameters. A stable acceleration with a stable light curve is consistent with a stable force geometry. A variable acceleration with a variable light curve suggests evolving activity or evolving spin. A variable acceleration with a stable light curve suggests measurement systematics or model mismatch. These comparisons provide a disciplined way to interpret the word non-random. The drift is non-random if it correlates with internal state. Another internal process is mass loss and fragmentation. If the object sheds mass, its moment of inertia changes. Its rotation can change. If it fragments, new surfaces can be exposed, altering activity and torque. These changes can produce sudden shifts in brightness and in residuals. In a simple model, such shifts look like anomalies. In a more complete view, they are consequences of a small body responding to heating. If such events occur, the correct modeling may require piecewise fits with different non-gravitational parameters before and after an event. Again, this is not new physics. It is a changing object. Therefore, in the path-not-random story, rotation and shape provide a bridge from external forces to observed drift patterns. They explain why forces are not constant in time and why measurement biases can be periodic. They also provide tests. If an object's motion appears to contain a pattern beyond gravity, rotation offers a way to check whether the pattern is tied to the object's internal clock. If it is, the pattern is likely physical, or at least tied to physical outgassing. If it is not, the pattern may be instrumental or geometric. The story remains calm because rotation is not exotic. It is expected. It is measurable. It is one of the reasons small bodies can show rich behavior in both brightness and motion without any need to attribute that richness to randomness or intention. A spinning, irregular body under sunlight will naturally produce repeatable variations. Those variations can imprint on residuals. The task is to measure the brightness distribution, and then decide whether the residual patterns match what a spinning, warming, possibly venting body should do. If they do, the path's apparent non-randomness is simply the visible trace of an internal state interacting with sunlight. If they do not, the remaining discrepancy either points to measurement bias not yet corrected or to a misspecified force model. In both cases, rotation remains the inward constraint that must be brought into the analysis before any strong claim is made about the nature of the drift. What observations can decide is the layer where the phrase does not look random either becomes a precise physical claim or fades back into an impression. This section stays with the deciding observations because without them, the same residual pattern can be explained in multiple ways. The first deciding observation is deep, high-quality imaging aimed specifically at detecting faint coma and tail structure. The method is to compare the object's radial brightness profile to that of nearby stars in the same image. Stars provide the point spread function. If the object's profile is broader, a coma is present. If it is identical, the object is consistent with a point source at that depth and resolution. This does not prove that no coma exists, but it sets a limit. Deep imaging repeated over time can show whether any extension appears as the object approaches the sun. If extension appears and its direction aligns with the antisolar direction, dust is likely. If extension appears and shows jet-like features, localized activity is likely. If no extension is detected under strong limits, then photocenter bias from dust becomes less likely, and any inferred non-gravitational acceleration is more likely to be a true nucleus effect. Imaging also allows nucleus-centered astrometry methods to be applied. If a coma is detected, coma modeling can be used to estimate the nucleus position. This can remove bias. Comparing orbits fit from raw centroid positions versus nucleus. Corrected positions can directly test how much of the drift is measurement and how much is motion. The second deciding observation is spectroscopy. Spectroscopy can detect gas species and can place upper limits when no detection is made. The choice of spectral range matters. For distant objects where water sublimation is weak, carbon monoxide and carbon dioxide become more relevant and are often targeted in the infrared. Optical spectroscopy can detect certain radicals and ions if activity is present. A detection of gas at a production rate sufficient to supply the required momentum flux supports outgassing as the cause of any non-gravitational acceleration. A strong non-detection, when translated into a low upper limit on production, can strain outgassing if the inferred acceleration would require more gas than the limit allows. This comparison requires an estimate of the object's mass, which depends on size and density. Therefore, spectroscopy is most decisive when paired with size constraints. The third deciding observation is thermal infrared measurement to constrain size and albedo. Visible brightness alone cannot separate a small, bright object from a large, dark object. Thermal emission provides an independent handle. If thermal observations yield an effective diameter, then the area-to-mass ratio can be bounded for reasonable densities. With size-bounded radiation pressure can be evaluated. If the object is large, radiation pressure becomes negligible. If it is small, radiation pressure becomes plausible. Size also enters outgassing and thermal recoil budgets. A small mass means a given thrust produces a larger acceleration. A large surface area means more sunlight can be absorbed, supporting more sublimation and more thermal emission. Thermal measurements can also hint at thermal inertia and surface properties, which affect thermal recoil. The fourth deciding observation is a well-sampled light curve that constrains rotation period and stability. A measured rotation period allows thermal recoil models to be more specific. It also helps interpret outgassing averaging. If the period is stable, spin is likely stable. If the period changes, torques and evolving activity are suggested. If the light curve is complex and non-repeating tumbling is suggested, which implies variable force geometry and complicates constant acceleration modeling. Light curves also help distinguish nucleus brightness variations from coma variations when combined with imaging. The fifth deciding observation is long-arc, high-precision astrometry from multiple independent observatories, ideally with consistent reduction standards. The key is that a non-gravitational signal becomes more robust as the observation arc lengthens. With more data, the orbit is constrained more tightly, and small residual drifts become clearer. Multi-observatory coverage reduces the risk that a systematic bias from a single instrument is driving the inference. Space-based astrometry can be particularly valuable because it avoids atmospheric effects and can provide stable point spread functions. Yet even ground-based networks can be decisive if the object is bright enough and if reductions account for Comet and catalog systematics. A sixth deciding observation is multi-wavelength position comparison. If the object's optical position differs systematically from its infrared position, dust or coma bias is implicated. If positions agree across wavelengths, the nucleus is more likely being tracked. This test is especially valuable when coma is faint. The seventh deciding observation is photometric behavior beyond simple distance scaling. If the object brightens unexpectedly, it may indicate activity or fragmentation. Such events can change both forces and measurement biases. Time correlation between photometric outbursts and changes in inferred acceleration parameters can indicate that the drift is linked to activity rather than to an unrelated force. Conversely, if a drift persists with no photometric changes and under strong limits on coma, sunlight forces become more plausible, especially if size is small. Another deciding element is the consistency of physical budgets. Once size is constrained, one can compute an upper bound on outgassing-driven thrust from energy limitations, an upper bound on thermal recoil from photon momentum, and the expected radiation pressure acceleration. If the inferred acceleration lies within these bounds, the standard mechanisms remain sufficient. If it lies above by a meaningful factor, The inference is either wrong or the object's properties are unusual in ways not yet captured. In a conservative narrative, this is where strong claims become justified or not. If the object is large, shows no gas or dust under strong limits, yet exhibits a robust, large, non-gravitational acceleration, then the standard explanations would be under strain. If the object is small or if activity is detected, then the explanations remain in place. Most often, the deciding observations do not produce a single dramatic conclusion. They narrow. Imaging may reveal a faint coma. Spectroscopy may detect a weak gas line. Thermal data may constrain size to a range rather than a point. Light curves may suggest a period, but with ambiguity. Astrometry may show a drift, but with a confidence level that grows over time. The synthesis then becomes a statement of what remains plausible. The phrase "path does not look random" can be replaced by a measured claim such as the orbit fit requires a small outward radial acceleration consistent with either weak outgassing or radiation pressure given a small inferred size, or the orbit fit requires a transverse acceleration consistent with thermal recoil given a measured rotation period. Or alternatively, the phrase can be replaced by a different measured claim, such as the apparent drift is explained by photocenter shifts due to a faint dust coma and nucleus-centered astrometry removes the signal. In either outcome, the non-randomness is understood. It is either physical or observational, but in both cases it is deterministic. This section therefore keeps the story in a practical frame. It does not promise a single answer. It specifies the measurements that decide among a small set of conservative mechanisms and that keep the interpretation anchored. It also clarifies the order of operations. First, ensure positions track the nucleus. Then confirm whether a drift beyond gravity remains. Then constrain size rotation and activity to test which forces can supply it. With that order, a path that does not look random becomes an opportunity to learn about a small body's physical state, rather than a blank space to be filled by suggestive language. A constrained synthesis of the track can now be stated without adding anything beyond what the earlier layers allow. This section stays with how a path that does not look random becomes a bounded account of motion, and it clarifies what would need to be true for the phrase to carry deeper meaning than gravity alone. The starting point is simple. Any real small body follows a non-random path because gravity is deterministic. The observed points fall along a curve because the object moves under the sun's pull, and because Earth's motion changes the line of sight in predictable ways. The first refinement is that an orbit fit turns that expected non-randomness into a specific trajectory with uncertainty. As observations accumulate, uncertainty shrinks, and the trajectory becomes stable. This stability can feel like pattern, but it is largely the convergence of estimation. Therefore, the first part of synthesis is to separate convergence from deviation. Convergence is expected. Deviation is the only part that requires explanation beyond gravity and measurement noise. Deviation is detected as structure in residuals. Residuals become meaningful when they persist across independent data, and when they remain after measurement systematics have been reduced. Therefore, the second part of synthesis is to say that the deeper sense of not random refers to residual patterns, not to the orbit itself. A residual pattern that repeats is a non-random feature. It means either a missing force or a consistent measurement bias. The third part of synthesis is to list the conservative sources of such non-random residuals. Measurement biases include star catalog systematics, atmospheric refraction effects, optical distortion patterns, timing errors, background contamination, and photocenter shifts due to dust and coma. Physical forces include outgassing, recoil radiation pressure, and thermal recoil. All of these are deterministic. None require unusual assumptions. Therefore, the existence of a non-random residual pattern does not imply mystery. It implies that the object and the measurement system together produce a repeatable mismatch with the simplest model, and that this mismatch can be localized by testing correlations with observatory geometry, wavelength brightness, and time. The next part of synthesis is to describe the most common resolution pathways. If deep imaging reveals a faint coma or tail, and if residuals align with the anti-solar direction, photocenter bias becomes a strong candidate. In that case, nucleus-centered astrometry can be applied, and the inferred drift may diminish. The path then remains non-random in the sense of being governed by gravity, and the apparent extra pattern is explained as a property of light distribution rather than nucleus motion. If spectroscopy detects gas, or if brightness behavior indicates activity outgassing, becomes a strong candidate. In that case, the drift is physically tied to sunlight and possibly to rotation. The residual pattern is non-random because the force is non-random. If no activity is detected under strong limits and size constraints indicate the object is small or low, mass sunlight forces become central. A radial outward drift can be consistent with radiation pressure. A transverse drift can be consistent with thermal recoil if rotation and thermal properties allow it. In these cases, the path does not look random because a subtle but deterministic solar-driven force is nudging the motion. This is not unusual in principle. It is a demonstration of how small bodies respond to light and heat. If size is constrained to be large and activity remains undetected under strong limits, and yet a robust large acceleration remains in nucleus-centered astrometry, then the standard conservative mechanisms become strained. This is the narrow case in which the phrase might begin to suggest that something unexpected is present. But even here, the discipline statement would not be that the motion is random or that explanations have run out. The discipline statement would be that under current constraints, the magnitude or direction of the inferred acceleration cannot be reconciled with the tested mechanisms. The next step would then be to question whether the acceleration inference is still contaminated by systematics, whether the size constraint is correct, whether the activity limits are truly stringent at relevant wavelengths, and whether the force model needs to be time variable rather than constant. In other words, one would return to measurement and modeling before declaring a limit of physics. The synthesis also clarifies what the path can and cannot say about intention or design. A non-random path in this context does not mean guided. It means measurable and deterministic. The incoming direction of an interstellar object is a vector resulting from prior motion through the galaxy. Detection selection can bias which vectors are seen. The Sun's motion can create preferred directions in the heliocentric frame. Therefore, even a clustering of directions would not imply guidance. It would imply relative motion and selection. Within the solar system, the path is a conic shaped by gravity plus small solar-driven adjustments if they exist. That is the full conservative account. The final part of synthesis is about what is gained. Even if nothing beyond gravity is required, the object provides a sample of an interstellar population and a test of orbit determination under faint conditions. If a small non-gravitational drift is required, it provides a physical fingerprint of activity or of sunlight-driven forces. If the drift is explained by dust bias, it provides a lesson in how Comet influence measurement. In each case, the phrase "does not look random" resolves into a more precise statement. The curve is gravitational. The residuals are either random noise systematic bias or a small deterministic force. This is the calm completion. It does not demand a single dramatic outcome. It reduces the story to the smallest set of claims supported by the data and the smallest set of mechanisms needed to explain any persistent drift. In that reduction, the track's apparent pattern is not a riddle. It is a constrained inference. It is a line through space shaped mostly by the sun, traced by careful measurement, corrected for the ways instruments and dust can bend light, and then compared to the known small pushes of gas photons and heat. If a push remains, it is measured. If none remains, the curve stands as it is. Either way, the path is not random. It is law-like, and the work of understanding it is the work of deciding which laws and which measurement realities are actually present in the record without adding extra meaning and without forcing the curve to carry more narrative weight than the sky requires. The wind down continues in the same steady way, with no need to push the language past what can be held. A path across the stars looks patterned, because motion under gravity is patterned, and because repeated measurements create a line where there was once only a faint point. When the orbit becomes stable, the impression of order grows. When residuals remain, the task is to learn whether the remaining order belongs to the object, or to the instrument to the nucleus, or to dust to a real force, or to a repeated bias. Each possibility is ordinary in the practice of measuring small bodies. Each is testable by the same quiet set of tools, deeper images, cleaner astrometry spectra, that search for gas infrared light, that constrains size light curves, that reveal spin and long arcs, that make small drifts either persist or dissolve. When those tools are applied, the phrase "does not look random" becomes less a feeling and more a set of numbers with uncertainty. A curve becomes an orbit. A drift becomes a parameter. A parameter becomes a budget compared against sunlight and mass and the limits of detection. The object continues on its open track, brightening and fading with geometry, leaving behind a trail of measurements rather than a trail of meaning. If the track can be explained by gravity alone, it is still a complete story. If a small additional push is needed, it is still a complete story because the push can be held within known physics until the data say otherwise. The sky remains wide and patient. The record remains in tables and images. The curve remains in the mind as a simple thing, a line that can be traced and checked and retraced until what seemed like a special pattern is understood as the natural pattern of motion, or as the natural pattern of light around a small body, or as the gentle pattern of sunlight acting on a fragile traveler for a brief time before it passes beyond easy reach and the last useful measurements settle into place.